Good morning to all of you. Let us start the today's class. So I welcome all of you for today's class. Today's class is based on a very important, part of our MSc syllabus. That is the physical methods of analysis. Okay, and the paper code you know already is 403. So till so far, what we have learned in our, the chemistry according to our different, syllabus, we have learned about our the identity of different molecules. We have handled the different molecules in the laboratory. Okay, we learned the techniques of preparations of different molecules, whether it is inorganic or organic. But one of the important part we didn't or not that much been exposed to is its identification. Okay, so whenever you are making something, we should have the intention to know that whether it is made correctly or not. So that's why we need to do some kind of analysis to get the confirmation regarding the molecule. Okay, and that's why the syllabus is designed in that way. So this syllabus is particularly focused on physical methods of analysis. So let us just quickly go through what is the aim of this particular course. Here actually the course outcome will be the learning on modern analytical techniques. Okay, so that is the main thing. What are the different techniques we should utilize for understanding a molecule? Okay, and secondly is what will be the applications of this technique in chemistry. Okay, one is to identify, and then what else you can do with these particular techniques. Okay, so analytical tools. So that are the two main focuses of this particular course. And now let me just quickly give out the what are the different unit we have, and then we'll be going directly our discussion portion. And the first unit of this syllabus is on diffraction technique. Okay, so that you can see here the diffraction technique. This is how particularly the crystallographic technique, okay, is utilized. So that part will be discussed. Second is you have the thermal methods. What are the impact of different temperatures on a particular molecule? Okay, so how the molecule will behave on applying different temperatures, and that part I think has been started by Sir Ganguly sir. And then we have another part is electron microscopy. So that will give the information, the regarding the molecules in its the structure at the how small the molecule is, and what are the you'll get a lot of information there. So mostly we'll have the different size and its behavior. If you know the size, if you know the porosity and all, you'll be able to understand that how the molecule will behave. Okay, and then you have the separation techniques, and this is you have been introduced a bit. Okay, and here we'll be learning a bit more details. And then we have the last one is the analytical spectroscopic methods. Okay, so there I think the atomic absorption, and we have the UV and other things are there, exapts and all. So those part will be taken care of. Now, among these, I'll be focusing on the separation techniques, the unit 4. And if you look at the unit 4, so we have here GC, HPLC, GPC. These are different techniques. So these techniques will be learning with its instrumentations and its application, how it will be helping in separations. So today what we'll start is, today we'll be focusing on HPLC, okay? What does it mean by HPLC? Its application and instrumentation, okay? So I don't know how much I'll be covering today. Will it be possible to cover maximum of this? But at least we'll be learning some fundamental parts of these HPLC techniques, okay? So without further delay, let us jump to the topic directly. Now, since we have the topic of separation techniques, let us know what are the different techniques we have been introduced till so far. I'll just summarize those things very quickly, and then we'll try to go to HPLC, and we'll try to learn why the need of HPLC comes, what benefits it can give over the existing other very simplified techniques, okay? So I'll just ask before going to that, what are the different separation techniques you have learned till so far? Can you just tell in your the practicals of this?
Chromatography.
What? A bit louder.
Sir, chromatography, column chromatography.
Column chromatography. Before any other technique you have learned? Column chromatography is definitely there, but a bit more simpler technique have you learned?
TLC, thin layer chromatography.
One is thin layer chromatography. Any other technique you have learned? A bit more simpler.
Paper chromatography, sir.
That is one of them definitely. Thin layer chromatography, paper chromatography, column chromatography. Do you have any other more simplified?
Separating funnel.
Kind of okay, but the technique we call it as the extraction technique, right? Where we use the separating funnel. So let me just quickly give the overview of these simplified techniques, and we'll be jumping to the HPLC, why we need HPLC, that will be coming to know. So as we know that one of the very simplified techniques is known to us is the solvent extraction technique, okay? Now here, what we do is, you may have a mixture, okay, and that mixture of compounds are of different property, okay? They have different behavior of being dissolved in different solvents, okay? Now, for in a simplified way, I can tell you, like say suppose you have a mixture of carboxylic acid, okay? You have a mixture of carboxylic acid, say suppose this is benzoic acid, and you have one ester, okay? So say suppose here ethyl benzoate, so here 1,3 is there. So ethyl benzoate, so that two are different molecules, right? And they have different behavior of being dissolved in different organic solvents. Since both of them are polar, so how we can do separation? They are definitely not highly soluble in water, and mostly they are very little solubility in water. So we can neglect the water solubility, okay? But how we can do separation of that type of mixture or mixed compounds from the mixture, okay? So what you do is, since both of them are polar, we can use a polar solvent first to dissolve them. So we can take a separating funnel we can put the mixture and we can put on polar organic solvent. Say suppose you are using the dichloromethane. Okay, so dichloromethane is a polar solvent. You can use the chloroform also, you can use the ethyl acetate also. Okay, these are the different polar solvents we can utilize to dissolve both of them. Okay, so they will be dissolved. Now what you do is you know that the property of carboxylic acid is it is acidic in nature. So if you use the mild base, so it can be converted to corresponding carboxylate, so anion, and I mean the salt. And then when if you make a salt, sodium salt or potassium salt, that has a very good tendency to be solubilized in water. Okay, so what you can do after dissolving the both of the compound, the mixture in DCM or any polar organic solvent of low boiling point. Okay, so what you can do is you add saturated sodium, aqueous sodium bicarbonate solution. So if you add sodium bicarbonate solution, what is going to happen? If you add sodium bicarbonate solution and do shaking, what is going to happen? The sodium bicarbonate is going to react with this carboxylic acid, and it will make the carboxylic acid to sodium carboxylate, and then sodium carboxylate will be coming to the water layer, right? So then what you can do is here, if you look at here, ethyl acetate, I mean the ethyl benzoate, after addition of sodium bicarbonate, if you do the shaking, ethyl benzoate that came to the organic phase. Okay, and in aqueous phase, sodium carboxylate or benzoate is there. Okay, now what you do, these two solvent, organic and aqueous, they are not miscible. According to their density, they will be separated out. If you use the low density or low dense organic solvent, that will be on the aqueous layer, and if you use the high dense, say suppose DCM or chloroform, they have more density over the water, so they will be at the down. So in this case, it has been shown that organic is at the top. That means that solvent may be the ethyl acetate or ether. So those kind of solvent which are less heavier than water, so lighter than water, so it will be at the top. And ethyl acetate, I mean the ester ethyl benzoate, it is coming to the organic phase, and the sodium benzoate, it is coming to the aqueous phase. Now what you do, you just open this knob and take this water part out, and separately you collect the organic layer in a different container. And then what you do is, the organic layer after collection, you just add some dehydrant, so dehydrating agent, say suppose anhydrous sodium sulfate or magnesium sulfate, do shaking to get rid of the tiny amount of water there, and then you do filtration and remove the organic solvent to get back the corresponding ester compound. Okay, and for water there, what you can do, since you have made the salt and salt is being dissolved here, like sodium benzoate, what you do, how you can get back that one? Who can tell? What is the technique to get back the carboxylic acid? What you can do here with this water layer? Who can tell? Who can tell quickly? How you'll get back the carboxylic acid? You have done your practical, so I think you should be able to tell.
Using organic solvent.
No. This is in water. Water part you have the benzoate, right? Sodium benzoate. So this is already water soluble. So if you use organic, it is not going to come out. This is already in a salt form, so it will not be soluble in any organic. That's the technique we are using to separate, right? So how you can get back the carboxylic acid? So you have collected the water part, right? So this is your water part where you have the sodium benzoate dissolved in the water. Okay. So now my question is how you get back the benzoic acid, because you have the benzoate, sodium benzoate. So you need to get back the benzoic acid. So what is the technique you will use to get back the benzoic acid? Who can tell? You have to use your brain quickly. So if you have the benzoate, you do acidification. So you add the mineral acid. So you can add HCl, right? Aqueous HCl, concentrated HCl. If you add it, do acidification, what is going to happen? Benzoic acid will be precipitated out. Okay, so benzoic acid will be formed. Sodium benzoate will be converted to benzoic acid in presence of high concentration of acid. So if you make the pH very low, so your acid is going to be precipitated out and cool down the mixture. So acid will be nicely precipitating out, and then you do filtration and dry it, wash it and dry it. Okay, so this is the way we do the separation. So based on the now solvent extraction, why we don't consider as to be the universal technique now? Because if it is sufficient enough, we didn't know. I mean, we didn't. We will not be in need of some other separation technique. Okay. So you have the limitations here. So similar type of compounds. Say suppose I want to separate 4-methoxy ethyl benzoate. Okay, and ethyl benzoate itself. So if you have a mixture of 4-methoxy ethyl benzoate and ethyl benzoate, so this solvent extraction technique will not help you to separate them out. Okay, because their behavior is almost similar. Okay, so solvent extraction technique is a good one, but that depends on what kind of compound you are trying to separate. Okay, so there should have some distinct behavior, then only you can do. Like you have the benzoic acid, you can easily convert it to salt, okay, and bring it to the aqueous layer. If you don't have that kind of things, it is very difficult. Okay, so say suppose you have pyridine and ethyl benzoate. So how we'll do that one? Okay, in that case you can maintain the pH to a certain extent, I mean in a proper way, so that the pyridine can be converted to pyridinium, and that can come to the aqueous layer. Got it? So this is the way we should utilize different associated techniques to separate the compounds by solvent extractions. Okay, so solvent extraction has its limit. It cannot be helpful. It is not universal, because it cannot be helping us to separate all different types of compounds from each other. Okay, particularly when a compound of similar nature, this technique is not going to help us. Okay, but we can have some other simplified technique, and we have learned that that is known as thin layer chromatography technique. And this technique is a nice one, so you can easily identify that how many different types of molecule you have in your mixture. Okay, and you can see, like if you have 3 different types of mixture having little differences among them, I mean 3 different of compounds in a mixture, okay, having little differences among them in their polarity or binding capacity. Okay, so we can utilize this technique. Okay, and what we do is here we use mostly the glass plate, having a coating on the glass plate of silica or some other solid substances. Okay, and that we call it as the stationary phase. Okay, and then we put the mixture drop there, and we try to run the plate in presence of a suitable solvent. Okay, and based on the binding property of the individual compound on the solid phase surface, they will move along the plate. So if you have tiny differences, they will be showing that they are moving in a different pace. Okay, so they'll be separated in the plate. And if you can get them separated out, like here you have blue color has moved very slowly. This red color has moved a bit faster than the blue, and the yellow color has moved even faster than the blue. Okay, so the binding property of this blue is more stronger than the red, and red is having more stronger binding property than the yellow. So that's why the yellow is moving very fast. And you have seen that here three different compounds are being separated from each other. Okay, and based on that you can do your overall separation. But remember, this TLC thin layer chromatography is an indication. It can give the indication how to do the separation. Okay, and that is being reflected, so you can utilize this technique to do the column chromatographic separation. Okay, and similar way of doing is the paper chromatography. It's just the same thing. Here, instead of using this glass plate and solid support, we have just the paper having good absorption property. Okay, so it can do nicely absorb the different the drop of the compound, and it can also behave the similar way. Okay, so here also you can do separation. Now we use the paper chromatography when if your compound is very polar. Mostly we use for the amino acid type of compound where we have the Zwitter ionic compound. Okay, that is better for getting some information about its separation in paper chromatographic technique. Okay, now in general other organic molecules we can do in thin layer chromatography. And the last one is getting information from them. These two techniques, thin layer chromatography or paper chromatography, we can, mostly it is the thin layer chromatography, we can think about the column chromatography. And here you have a glass column having a stationary phase, which is generally the silica we use. And then what we do is at the top of this silica column, we put the compound being adsorbed on silica. Okay, and then what we do is we use the mobile phase, means the solvent, suitable solvent, which is what type of solvent we should use, that is being guided by these thin layer chromatographic technique. Okay, so if thin layer chromatography, you see the suitable solvent which is able to separate them of different compounds. Okay, so that kind of solvent you can use, and let the solvent, we generally add the solvent here, and it will flow to this direction, and we collect the solvent here. So what we see is that based on the binding property, which will be less binding capacity, that particular compound will be moving faster and it will be coming out fast. So here if you see, you have the blue kind of, the sky blue kind of compound is coming faster way, and then you have after its separation, the red has started coming, and then finally the dark blue, it has started coming. So in this way, just being guided by thin layer chromatography, you can do the column chromatographic separation for large scale of mixture. So thin layer chromatography is just to get the idea for how to, idea for the suitable solvent, and then we do the separation by column chromatographic technique. Okay, now let me just come with the need of HPLC. Okay, how the evaluation, evolution of column chromatography has been, the evolution of HPLC has been done, so from column chromatography to HPLC. So we'll come to know in details of HPLC. Just let me give you some of the basic informations of column chromatography. So in liquid chromatography or the column chromatography, generally we do in glass columns of diameter 1 to 5 centimeter. Okay, and if you talk about the length, it is around 50 to 500 centimeter. Okay, and the solid stationary phase, we use of a variety of solid stationary phase. It can be silica, it can be alumina of different properties, maybe acidic, basic, neutral, okay, based on your need. And we use generally the diameter of the particle of the solid stationary phase particle, okay, of 150 to 200 micrometer, okay, in this column chromatography. Why we use this particular size is that if you have the silica packed, and if you don't have a suitable pore size, I mean this particle size, what will be the problem is, if you add solvent, the solvent will not flow very fast. So if you have a little bit suitable pore size, so what you can do is you can have the different kind of packing. Okay, so you have different kind of packing of the particle, and if you look at, I'm doing some kind of packing. So here you have the gap between the two particles, right? And these gaps are required for smooth movement of the liquid phase. Okay, so it's found that 150 to 200 micrometer is suitable for doing the column chromatographic separation of suitable particle size of the stationary phase for the efficient separation. Okay, but generally we find is that the still it is a long time taking process, right? So if you just allow the solvent to pass along the gravitational force, so what we'll see is that it takes even more than 2-3 days for doing even only 1 gram of compound reaction mixture separation, right? So we need some kind of modification. Okay, now one more thing is that if you do decrease the particle size, the interparticle gaps will be very less. So particle will be well packed, and that will further decrease the movement of the solvent. But what we can get the benefit of this decreasing of particle size is that the separation will be more nice. Okay, so you know that if you decrease the particle size, okay, your overall the surface area is becoming it is increasing. Okay, by decreasing the particle size, so say suppose you have a mass of 1 gram of particle, okay, a lump of 1 gram of particle, and you are breaking it to very dust particle, and that is also the same mass. So what we will see is that you are doing the increasing, you are increasing the particle surface area actually. Okay, and if you have more surface area, then your compounds are getting more chances to be interacting with the particle surface, and it is being connected. Okay, it is being nicely interacting, and so your movement of the particles will be more ordered way. So your separation will be more nice. Okay, so if say suppose you have 5 molecules, and you are getting the active surface for interaction is, say suppose 4. So you have 1 molecule is not able to get interaction, so they'll just pass very fast. Okay, but if you allow the particle size, I mean, in such a way that almost all of the the molecules can interact, then your particle movement, the movement of that molecule will be very in systematic way, so you can do the separation nicely. So that's why for in general column chromatography, the main flaw is you have the efficiency of separation is not that much. If you are having the particle, I mean the compounds of very close RF value, then the separation will not be so easily be done in regular column chromatographic technique. And in that case, we need to increase the efficiency, and for that we need to lower down the particle size, and the diameter 3 to 10 micrometer is found to be the most suitable particle size for separation of any kind of different compounds having whatever RF value is. Even the RF value are very close, say suppose 0.1 differences, okay, even that will be able to be separated in the this kind of small particle size column, okay. But the biggest problem here is your solvent will not move so fast because you are decreasing the particle size. So I mean the gaps between the particles are decreasing, so solvent cannot move easily. So this technology required sophisticated instrumentations, okay, and the new sophisticated instrumentation is being, I mean, is being is discovered and is called as HPLC. Okay, now let us come to know what is HPLC. The full form of HPLC is the high performance liquid chromatography. Earlier it was being called as high pressure liquid chromatography, because here pressure is one of the important part is utilized, okay. So some HPLC pump is being used there. So I'll come to the more details of the instrumentations. There you will know what are the different things are there. But for the time being, you just know that HPLC is the abbreviated form of high performance liquid chromatography. Is one of the most widely used techniques for identification, quantification, and purification of mixtures of organic compounds. It's just written organic compounds, but even the inorganic complexes are that can also be separated if they have suitable solubility in different organic solvents too. Okay. Now in HPLC, like other chromatographic methods, components of a mixtures are partitioned between an adsorbent stationary phase and a solvent mobile phase. So it is just the same like column chromatography, but it is an advanced technique. So it is also having two things like the stationary phase and the mobile phase. So the stationary phase is made of very small particles contained in a steel column. Now here you have a steel column, and due to the small particle size, the pressure is required to allow the mobile phase to pass through. So the stationary phase, for stationary phase movement, the pump is required. So HPLC pump is required. And there are a wide variety of stationary phases available for HPLC. In the lab, generally, the stationary phases used are of two types. We call it, one is normal phase and another is reverse phase. So based on that, we have the two types of column. We call the normal phase column and we call the stationary phase column. Okay. What is normal phase and what is reverse phase column, that will come in a minute. So let me just tell that one. The normal phase is normal phase column. Generally, it has the stationary phase as the silica. Okay, silica, and the reverse phase column, it has stationary phase silica, which is modified. It's not just the normal silica; it is the modified silica, in which 18 carbon hydrocarbon is covalently bonded to the surface of the silica. So you have the silica is having the C18 hydrocarbon connected. Okay, it's modified. The surface is becoming more hydrophobic in nature because you are putting the long chain of hydrocarbon, C18 hydrocarbon. Okay, so the most commonly used HPLC stationary phases are hydrocarbon bounded on the silica surface. Okay, and in general cases we use the reverse phase column for separation technique, but normal phase HPLC is also there. You can, based on your compounds, we use that one, and in a course of our discussion we'll be learning that when we should use the normal phase column, when we should use the reverse phase column. Okay. So normal phase chromatography. So normal phase chromatography, the first kind of HPLC that came is developed. Okay, and in this method separates analytes based on their affinity for a polar stationary surface such as silica. Hence, it is based on analyte ability to engage in polar interactions. Okay. So what are the polar interactions we know? We know that the hydrogen bonding interactions and the dipole-dipole interactions. Okay, so that are the two important interactions are kept in mind, and this column has been developed. Okay, so now what we see is that in normal phase HPLC, a non-polar, non-aqueous mobile phase is generally utilized. Okay, so non-polar, non-aqueous mobile phase. Non-polar, I'll tell, like here, non-aqueous in that sense, the chloroform, but chloroform is non-polar. I mean, it is highly polar, but non-polar in that sense, polar aprotic. Okay, so it's better to write the polar aprotic, non-aqueous mobile phase. Okay. Sometimes the non-polar solvent are also utilized. Okay, and works efficiently for separating analyte readily soluble in non-polar solvents. Okay, so adsorption strengths increase with increased analyte polarity. So if you have more polar solvent, if you have more polar compound, that will be more strongly binding on the silica surface. So that is the thing here told, like adsorption strengths increase with increased analyte polarity. The interaction strength depends not only the functional groups present in the structure of the analyte molecule, but also steric factors are there too. So, and when you have particularly the steric kind of things, it helps in case of like isomer kind of structural isomer, that kind of mixture. If you have, you can do separation. So the effect of steric hindrance on interaction strength allow the this method to resolve structural isomer. Okay, so structural isomers, for that case you have steric factor is more important. Okay, so based on that the separation happens. Now the use of more polar solvents in the mobile phase will decrease the retention time of the analyte. So if you use more polar solvent, so that will help the compound to move faster. The polar compound will be moving faster. So that means your retention time means at what time it is showing the peak of its appearance. Okay, that time will be less. So the retention time will be decreasing. So we'll decrease the retention time. Whereas more hydrophobic solvent tend to introduce slower elution, and your retention time will be increasing. So that means you can play with the different solvents, and based on their polarity, whether it is more polar or less polar, you can play with the retention time of the compound. Okay, so the very polar solvents such as trace of water in the mobile phase tend to adsorb to the solid surface of the stationary phase, forming a stationary bound layer, which is considered to play an active role in retention. So you have a layer formation of the water on the stationary phase. Okay, and then that will have, that will make a different interactions of the compound with the stationary phase. If you have a kind of layer on the stationary phase of water, then the compound is not directly interacting with the stationary phase, so it has the interaction with the water. So that means it will behave differently. So this behavior is somewhat peculiar to normal phase column chromatography, because it is governed almost exclusively by an adsorptive mechanism. That is, analytes interact with a solid surface rather than with the solvated layer of a ligand attached to the solvent surface. Okay, so your behavior of the compound will be changing based on what is the nature of your stationary phase now. Okay, so if you use water, you will have the stationary phase is becoming modified because it is having a water layer on its surface. So the adsorption chromatography is still widely used for structural isomer separations in both column and thin layer chromatography formats on activated silica or alumina support. So stationary phase, you can use the silica or alumina, but they are still used for separation of structural isomer too. Okay, so quickly I'll go to the reverse phase and we'll stop here. So reverse phase chromatography, the nonpolar stationary phase and aqueous moderately polar mobile phase is used in reverse phase HPLC. So remember, it is just the opposite to normal phase. Here the nonpolar stationary phase is used and aqueous and moderately polar mobile phase is used. So there your stationary phase was more polar and mobile phase was relatively less polar. But here your stationary phase is less polar, means non-polar, and your mobile phase is moderately polar or polar. Okay. So one common stationary phase in a silica which has been surface modified with RMe2 SiCl. So this R can be different size, means different hydrocarbon. Okay, where R is a straight chain alkyl group such as C18H37, that is the 18 carbon hydrocarbon, and or C8H17. So this C18 and C8, those kind of hydrocarbon is being attached to the silica surface. So with such stationary phase, the retention time is longer for molecules which are less polar. So if the molecule is less polar, so it will have the more strong hydrophobic interactions, okay, with this modified stationary phase, and that will move slower, okay, while polar molecule will leave it more readily. So in generally what we do is we do separate the polar organic compounds, right? And that's why the reverse phase column is more efficient in HPLC to separate the polar compounds, okay, over the non-polar. Okay, so that suppose you have the carboxylic acid, and if you try to do, I think some of you have the experience when you have done the column, I mean the TLC. If you have very polar compound and mostly with carboxylic acid, you see it will not move through the TLC plate, right? So it is very difficult to separate that one. But if you take the reverse phase column, okay, or reverse phase silica and do the TLC or do the HPLC, what you will see is that your carboxylic acid is moving very faster than the non-polar compound. Okay, so you can easily do separation. So based on your need, what kind of compounds you are trying to separate, you can choose your column and do the separation. So increase in retention time by adding more water to the mobile phase, thereby making the affinity of the hydrophobic analyte for the hydrophobic stationary phase stronger relative to the now more hydrophobic mobile phase. Yes, so you can utilize water here and do some modification to the nature of the movement of your compound. So decrease retention time by adding more organic solvent. So you can do modify the retention time by adding more organic solvent to the eluent. Okay, so reverse phase HPLC is so commonly used that it is often incorrectly referred to as HPLC without further specification. So generally, when we talk about the HPLC, it generally utilizes the reverse phase column. So it is so oftenly used that we don't even bother to mention the reverse phase. We just tell it as HPLC. Okay, so because we are always having the intention to separate the more polar compound. Okay, that is the thing. So reverse phase column chromatography operates on the principle of hydrophobic interactions. As you know, the modified surface of the solid phase is the hydrophobic chain. Okay, having the hydrophobic chain, so which originates from the high symmetry in the dipolar water structure. Okay, now again we have the reverse phase HPLC, which allows the measurement of these interactive forces. The binding of the analyte to the stationary phase is proportional to the contact surface area around the nonpolar segment of the analyte molecule upon association with the ligand on the stationary phase. So these things, if you just go through, you will be understanding what I told till so far. So these you can correlate and you can understand. Just one thing I will tell you here: the energy released in this process, okay, is proportional to the surface tension of the element. So water has the surface tension 7.3 × 10⁻⁶ joule per centimeter square, and methanol have less surface tension, and to the hydrophobic surface of the analyte and the ligand separately. So you have the relations. There is an importance of the surface tension of the interactions. Okay, the more the energy will be released this process when it is interacting. So that depends on what kind of surface tension you are providing. The retention can be decreased by adding less polar solvent. Okay, say suppose in place of in place of water you are using less polar solvent, methanol, acetonitrile. So your retention time will be decreased into the mobile phase to reduce the surface tension of the water. So when you use the pure water, you will have high surface tension, so molecule will move. You have more retention time. I mean, it will take more time. And if you use methanol or acetonitrile, you are actually decreasing the polarity of the water, and so as to the surface tension. So your retention time is going to becoming less. Okay, ultimately you are moving from high polar to less polar, and if you have more hydrophobic character, less polarity, you have more interaction. So your retention time will be if you have more hydrophobic character, your retention time will be more in case of less polar compound. Okay, but more polar compound, your retention time will be less. Okay, so this is the overall message. So in the next class, what I will do is we'll be discussing how to operate, or how the peaks will come, what are the chromatogram, how we can do monitoring. So all those things, the calculations and all, peak area, okay, all those things we'll be learning the next class, and following classes we'll be learning the instrumentation part. Okay, so I'll give this one to your Google Classroom. Go through and just try to understand. If you have any difficulties, you discuss in between, or any time you can contact me. Okay, so I think you have another class, so let us stop here, and I'll request the seer to send me the attendance, and we'll meet in the next class soon. Okay, so thanks for joining today's class.
Thank you, sir.
Thank you,
Thank you, sir.
Thank you, sir.